Let's take a look at fractional distillation. Remember, simple distillation is one vaporization condensation cycle. Let's say that we're 85% B and 15% A. So that's this point right here. Okay, so let's see what we collect. You can see, you can cheat a little bit because I wrote it down there, but let's come up here. That's your boiling point, right? At that percent composition, that's your boiling point there. And then now we have this liquid vapor condensation cycle. And now we're coming down here. And this is what we collect. So this is what we get off of the column. So what's collected in here is 30% A and 70% B. Now remember, I said we could take that and we could distill this again. So we could do a 70% B here, 30% A. So that's what we're going to put in this. So we're taking this stuff and we're going to distill it again. So it's our second cycle. So there's our first cycle. Here's cycle number 2. There's cycle number 2 here. So in this case, we're starting off right here. Okay, we're going to heat it up, heat it up, heat it up. It begins to boil. We hit a liquid vapor condensation, and now we're going to collect right here. And for this, I'm just going to call this 85% A, 15% B. We're just eyeballing it, right? And now that's what we've collected here. So that now is 85% A, 15% B. Notice that we're getting more enriched here. So with simple, if we wanted to purify it even more, just to drive home this point, now we're 15% A, 85% B. That's in here. So we're starting off somewhere around right there, coming up, over, and down, and we're at that point right there. So we could call that 90-10 if we wanted to. Again, we're eyeballing it, so 90 A, 10 B. All right, so here you have 90% A, 10% B. All right, so we could continue this on and on and on and on, right? And we would become more and more and more pure. That's time consuming. Simple distillation takes time. And to carry this thing out over and over again, it's going to take, a couple lab periods, maybe 3 lab periods, depending on how many times you want to do this. The volumes are going to get smaller and smaller too, so it's kind of a hard process to try to purify something really well using simple distillation. Now, simple distillation tends to work really well if the boiling points of the compounds are very different from each other. If they get closer, then that separation has to be repeated over and over again. The distillation cycles have to be done over and over again. And that's where we use something called fractional distillation. So here's what happens with fractional distillation. Let's look at a macroscale example of this. So down here below, we're going to start off with our 85% B, 15% A. So we start to heat it, and all that stuff. Vapor comes off of that. Okay, that vapor comes off. So here, let's follow along on the side here. So that vapor comes off, right, as we boil. So we're starting here. This is your 85% B, 15% A. So we heat, right, and it starts to boil. So that vapor comes off, and it comes up into this column. And in the column, we put like a mesh. The mesh is there to help support the condensed vapor. So if it was just a tube, the vapor would condense and gravity would pull it down in there, right? Because it's just a tube. Instead, there's like a mesh in there. So that vapor comes up and it condenses. And let's just say that it condenses here first. Okay? So as it condenses, we would have this composition. But we're not going to collect it. We're going to leave it in the column. And that's what we said was, right, our 70-30 or something like that, right? So now what we have here is that's your 70-30, right, B, A. So what we end up with here is a 70-30% composition that's basically this liquid that's being held on our column here. Now again, the column's full of a bunch of mesh or something like that, but just to make things easy, let's just make that line right there and just say it happens right there, right? Just to make this easy. And again, we know it's 70-30 because we could follow this down here to our x-axis, and that's what we saw, that 70-30 there. Right, now this compound has a boiling point, right? The 70-30 has a new boiling point. What we're left with here is more vapor, right? That vapor is going to have a higher boiling point, so you have a second kind of surge of vapor coming off of this. You can think if it's continuous, but imagine that there's another burst of vapor. That vapor comes up here, right, and it's hot. It hits that liquid, and it causes that liquid that's there to turn into a gas. So we get another little distillation right there. So what happens is we kind of redistill that, but that's in the column, so we never left. We're right here. And now we have another liquid gas condensation cycle. So then what happens is that vapor then moves up to this point right here. And I'll just pick another color. And now we have a new percent composition there. So what's the second step? So second step composition, well, we'd collect that vapor, right there. So if we wanted to know, we'd come down and we'd look right there at our axis. And, we'd call this, I think we call it 85-15, right, in our other example. So here we have 85% A, 15% B. And again, the numbers don't really matter, but we're more enriched. Okay, but we're not going to collect this. It's staying in the column. And now we have some liquid there. And then what happens is we have more vapor coming off, right? There's liquid still here, right? So that green vapor that came off here condensed at step number 1, and it caused the stuff that was at 1 to go to number 2. Now we have more coming up here, right? We have the third burst of vapor causing step number 1 to turn into gas, which is hot gas that moves up to step number 2, which causes that to move up to step number 3. So that comes over here just like that. That's this, and that would come over, and we'd figure out its percent composition by looking down there. And we could call this 90% A, 10% B. You get the point here. Right, so over time, the vapor just kind of makes its way all the way up through many, it's not 3 or 4 little cycles here, through many cycles, all the way up to the very top. But every time we encounter one of these liquid vapor condensation cycles, we get one of these things here. These lines here that come across are called steps. Right, so each one of these is a step. Right, so we come down, this would be another one, so on and so forth. And eventually you're over here at something that's very pure. Right, 95% A, 5% B, for example. So that's the idea behind fractional distillation, is you get many simple distillations occurring within the column, essentially. And the principle is the same, essentially, for microscale, except the glassware looks a little bit different.
This diagram over here really kind of explains what I was just talking about. So if you look down here at the bottom, you have this liquid that has a 5% composition of compound A with a boiling point of 87. So the first vapor that comes off of this has a composition of 20%. So that's where you've gone up and over and down on your little vapor condensation cycle curve. Now that 20% condenses, and they're just saying here, like my example on the last page, that it happens to condense right here. So that's your liquid at 20% A, has a boiling point of 78. More vapor comes off of this, and when that hot vapor comes up and touches that liquid that's at 20% A, it causes it to vaporize. So you get another liquid vapor condensation, and that vapor that comes off of the 20% is enriched more in A, and it has 50% A. that travels up to this second step here. And that's it condenses, theoretically right there. That's your 50% A. It has a lower boiling point, right? So another kind of set of hot vapor comes off, and it causes the vapor at this position to vaporize, which comes up here and causes that 50% liquid composition of A to vaporize. And the vapor that comes off of that's 80%. It travels up, condenses here, right, at our our third step, really. And then it has a lower boiling point. Right? And when it vaporizes, it comes off as 95%, and so on and so forth as it kind of comes up that column.
Now, in a microscale setup, what we have is sometimes we use a jacketed condenser, but we don't run water through it, because if we ran water through it, would cause the liquid to condense. Instead, we use it to insulate because it's insulated by air. And the other thing that we often do is we wrap this thing with aluminum foil to keep it kind of warm. You can use glass wool in there too. And then the third thing that we do, if you leave it open, the vapor just hits the wall and comes back down. So what we do is we fill it up with a mesh. So we use like a steel mesh to shove it in there. But the same thing happens here. You have many liquid vapor condensation cycles. So fractional distillation, it takes longer because that vapor has to make its way all the way up to the top before it starts condensing on your glass here, right? A couple other points about fractional distillation that I want to point out to you here. The number of liquid vapor condensation cycles, those are the steps, if you remember, that occur in a distillation. Let's talk about that. It's related to those horizontal lines, right? So those horizontal lines that are drawn out on those vapor composition diagrams, remember, are steps, right? We talked about that. So simple distillations often, not always, but often will have just one step. Fractional has many theoretical plates. So these theoretical plates and these steps, those are the same thing. Okay, a plate is something that's flat, right? And I mentioned this before, but recall that the closer the boiling points between two compounds, the more theoretical plates are required to separate the components of a mixture. This is why simple distillation is good for separating compounds that have larger boiling point differences. One of the terms that you may see if you go on in chemistry is something called HETP. It's a height equivalent to one theoretical plate. It's a measurement of the column efficiency, essentially. So when you buy a column, you can buy columns that have lots of HETPs. Depending on what you're trying to do, you may want to have a column that has lots of plates.